so degree field navigation with Dijkstra's algorithm. Okay, so the first task of our ZeroRobotics game was to navigate the debris field. So these are two screenshots from inside the simulation. The one on the left is of a 2D game, and the one on the right is of a 3D game. And so the main goal during the ZeroRobotics, during the debris field navigation, is that you want to take your sphere, which is in blue on this side, and you want to navigate through the debris field and get to this side where the red sphere is at. And obviously what's in your way is the debris. And you have different sizes of debris. You have the green, the purple, and the orange. And the orange has the highest percent of thruster loss, and then the purple has a little bit less, and then the green has even less. And so we'll mostly be focusing on the 2D version instead of the 3D version, because the 2D version is simpler for Dijkstra. So our approach to solving this problem was to use a graph. A graph is made up of vertices, you can see here in black, and edges, which are the purple lines connecting the black vertices. And the way I want you to think of this is kind of like a map of your neighborhood. So these black vertices represent different houses. So house 0 is your house. Then you have friend 1's house over here, friend 2's house over here. And between each house is a road connecting, each house. So to get to friend 1's house from friend 0's house, you have to travel along a road of length 2 miles, and to get from friend 1's house to friend 3's house, you have to travel along a road of 6 miles. And so the question we're trying to ask when we're finding like a shortest path in this graph is we're saying, what's the shortest path between using these nodes and using these roads to get from, for example, your house to friend 5's house? So does anyone think they can tell me what the shortest path in this graph is from friend 0's house to friend 5's house? Any ideas?
Use your hands. Yeah.
Remember, we're trying to take the roads between the nodes. Yes?
Go around the bottom?
So that path has length 5 plus 2 plus 3, which is 10. But I'll give you a hint, there's an even shorter path with like 9. Yes?
You go 0, 1, 1 to 2, 2 to 4.
Yes. So the shortest path is 0, 1, 2, 4, 5, and you can add all the weights, and that'll give you a path of length 9. So as you can see, even thinking about this is a pretty difficult problem, and it becomes even more difficult when you have hundreds of vertices or even thousands of vertices. And that's why we use Dijkstra's algorithm to quickly find the shortest path. So now you're probably wondering, how do we apply Dijkstra's algorithm to our debris field navigation problem? So we'll take a map like this and we'll overlay it over our debris field. So we have, again, all the vertices, this time in red, and we have the black lines connecting the vertices. And so what the vertices are is they're like saying, they're telling the sphere, these are all the places on the debris field you can go. So this sphere can go here, it can go here, it can go here, and the ultimate goal is to get it over here. And the way it gets there is by following these black lines. So once we have a graph, once we tell the sphere, these are all the places in the debris field that you can visit, and these are all the ways you can get there, then we can simply run Dijkstra's algorithm on this graph and find the shortest path from the beginning to the end. But now the question becomes, how do we set up such a graph so that if you can find the path, then Dijkstra's algorithm will also be able to find the path. So that's what we're going to talk about next. And the first thing we got to do is we got to kind of simplify the problem. So we have currently a sphere, or a circle, and it's navigating through a bunch of other circles, and we're going to try not to touch too many of the other circles. But to simplify this a little bit, we're going to instead take the sphere and we're going to call it a point. And instead, we're going to add its radius to all of the other obstacles and form these light blue circles. So now you see, if the sphere is moving around and the point is moving around, and it stays outside of these light blue circles, then the original sphere won't crash into all the obstacles. And so what we want to do now is we want to set our vertices, right? So the vertices are going to be all the places along the perimeter of the obstacles. Those are all the places where we're telling the sphere you can visit those places. We're saying you can visit the outside of every obstacle, and just an intuitive idea of why we want to set the vertices to be here is that this way the sphere has a way to navigate around every obstacle, because the sphere can go from here, it can go to this point on the sphere, and then it can go around and get to the other side. But obviously there's an infinite number of points on the perimeter of every sphere, so we can't use circles itself. We have to use a polygon to approximate these circles. So for example, we could use squares. But going back between these two, you see that the squares are a pretty bad approximation. They take up a lot more area than the circles themselves. So we can use a polygon with more sides, for example, a decagon, and that forms a much better approximation. So just to recap, we've now told the sphere that all the places you can visit, all the vertices of our graph that we're going to run Dijkstra's algorithm on, those are all the vertices of these polygons, of these decagons. So now the question becomes, how do we set the edges and the weights between these vertices? And so this is the same graph as before, but now I've drawn in a couple of the edges. And so I want you guys to take a look at a couple of these paths. So let's take a look at this path from the beginning all the way to the end. This is the shortest path to get from the beginning to the end. It's just a straight line. But you can see it's probably not a very good path for our algorithm because it's going to overlap with 3 of the spheres, and that's going to cause a lot of thruster damage, and we don't want that for the later phases of the game. So instead, maybe we would take a path like this, going up and around like that to the end. Now that path is much longer, but it doesn't hit any of the spheres, but it's still pretty long, and maybe time is also an important factor. So maybe we don't want the longest kind of path. Maybe we want to compromise between the two, and you can look at this path in the middle here, which it overlaps one of the smaller debris, which is going to cause a little bit of thruster damage, but this ultimately will probably be the best path. So you can see that the way we want to set the edge weights is we want it to be a function of both the length of the path and the amount of thruster damage that the sphere will take when traveling along this path. And that is exactly what we do. The edge weight, just to recap, is the length of the path times some parameter alpha1 plus the thruster damage that the sphere will take traveling along that path times some other parameter alpha2. Now, having these parameters alpha1 and alpha2 lets us tune Dijkstra's algorithm in order to meet different phases of the game. So for example, if we wanted the sphere to get to the other side of the debris field very fast, and we really didn't care much about the amount of thruster damage that the sphere took, we would tune up alpha2, alpha1, and tune down alpha2, and this way the sphere would prioritize a path that is shorter and maybe doesn't take as much thruster damage. And conversely, we could do the opposite if we wanted a path that avoided a lot of the spheres and didn't take a lot of thruster. And finally, the generalization to 3D. So because we were mostly focusing on the 2D version of the game, we would instead use polyhedra instead of polygons in order to approximate these spheres, which were earlier circles. But the Dijkstra's algorithm was actually a little more useful in the 2D phase when we actually wrote the code, because approximating these spheres in 3 dimensions is very difficult because it requires a polyhedra with a lot of points, and we didn't have this kind of code space on the actual sphere because there's not a lot of memory for it. So that is Dijkstra's algorithm in the debris field, and now we'll go to Mayor for math and physics in rendezvous and hooking.
Thanks, Deep. Okay, so math and physics in rendezvous and hookup.
Excuse me, sorry, we came 5 minutes late, so we missed the intro. Could you just give us the layout? Like, what are you starting with in this math and physics?
Oh, this is, I'm just curious now. I'm gonna talk about what we,